I came up with the phrase polymorphic contexts, which I hope will be famous from now on. So the goal of this talk is to show you that if you have lazy evaluation, actually something like system F, the type system, is not enough. We want to have something extra because there are useful programs which we want to write, but which we can't type check and type using system F. Then I'll also show you that the Utrecht Haskell compiler happily accepts this extension, which I don't know whether it came as a surprise, but also was very happy when they showed him that this worked. And finally I'll show you how to, with some extra work and bookkeeping, you can do something similar in GHC. That doesn't look as nice as it looks in the UHC, but it shows somehow that the extension I'm proposing is not completely unsound. Or the GHC also makes serious mistakes. In languages with lazy evaluation, and this looks like what we call in Dutch an open door, which we kick in. If we look at a function, we say a function takes arguments and returns results. Well, this is what every high school student will agree with. And I add to that a context is something which takes results and provides arguments. So this is you may think about the context as the place where a function is called. Well, normally this second line is a kind of not really important, but I claim that in the view of lazy evaluation, it really is important. And to start off, I will show you a couple of programs and then finally show you that by taking a number of completely reasonable steps, I end up with a program which does not type check. And to show you kind of what's going on, I start with this RepMin problem. Who does not know the RepMin problem? It's always surprising. It's the most famous program which if there's something like lazy evaluation being taught, then people come up and say, oh, you can have infinite lists. That's not really exciting, but then they show you the RepMin problem, and then people go home and say, this can't be true, and are completely surprised. So the goal of the RepMin problem is, I have a data type. It's a binary tree, which has integers in the leaves, and I write a function which takes a tree and returns a tree. But this tree, the leaves in this tree, the value which is sitting in those leaves is the minimal value of the leaves in the argument tree. And what the RepMin problem is doing, it says, well, I have an auxiliary function, RepMin prime, which walks over the tree, returns two things, which is the minimal value, and the result I'm interested in, the tree which contains this minimal value. And then I take this minimal value and pass this back to this RepMin as the minimal value to be taken as the value to place in all the leaves. So now if you look at the RepMin prime, so if we take a leaf and this is the new minimal value, then I return the V which is living in this leaf in the argument tree, and I construct a new tree which is a leaf again because I'm inspecting a leaf, so I produce a leaf and take this minimal value and use it to construct a tree. And otherwise, if I have a binary tree, then I walk over the left tree, I walk over the right tree, you get the left minimum and the right minimum, a left tree and a right tree as a result. I combine the two minimum to compute the minimum of those two trees, and I construct the resulting tree. So in all the programs I'm going to show you is kind of this same pattern. So I show you a lot of Haskell, but it's kind of always the same Haskell with small changes. So the essence, what I'm doing here, is this value n, which is coming out, I'm passing back in as a result. So if I look here at what the context is doing, it says it takes results and it provides arguments. So that's what's going on here. So now for those who think this is extremely complicated, let me show you a kind of strict implementation, an equivalent implementation, but then in a strict language, or in Haskell again, but which is strict, which performs the same computation. What I do, I define an intermediate representation which contains an integer and a function which, if I pass it an integer, will construct the tree. So this function which I'm returning, this redbean2 says walk over a tree, I compute the minimal value m, and the function which is called reconstruct, which kind of remembers the shape of the original tree, and then I pass this m, which is computed here, to this reconstruct, and then it reconstructs a tree of the same shape as the original tree, with this minimal value in the leaves. So this code is kind of boring. So what we say in attribute grammar terms, that this is a two-pass attribute grammar. You walk once over the tree to compute a minimal value, and once you have this minimal value, you walk over the tree once more, and you construct the result.